Today I am with the engineers, Hice, Muñoz, and Nina Reyes to talk about the new advancement in the development of electric motors. What can you tell me about these motors?
The global shift toward variable frequency drive drove a search for higher efficiency. We found that even high quality induction motors still lose about 20 to 35% of their energy in the rotor. To solve this, the synchronous reluctance motors was created. By removing the rotor bars, it effectively eliminates those losses. However, to achieve the absolute best performance, we now have the permanent magnet assist synchronous reluctance motor. It combines the standard synchronous reluctance motors designed with magnets for superior results.
Okay, but what are its characteristics? How does it work? What are its advantages? What are its limitations? To explain that, I first need to start how it's work. The synchronous reluctance motor generally consists of a ferromagnetic core in the stator, using the same type of termination of in a induction motor. And in some cases, the same stator can be used to reduce core losses whereby hysteresis or eddy currents. The stator is built using very thin lamination or steel or sterilized. Typically, the lamination have a thickness of about 0.35 millimeters. As for the rotor, it is also built using lamination shaped like this, stacked one by one along the shaft. This lamination includes barriers that create paths of high and low magnetic reluctance. Well, then how does this help reduce current losses and increase permeability?
In this machine, the main axes are defined. The direct axis corresponding to the direction of the highest performance, at the quadrature axis associated with the lowest performance. The motor torque is generated because the rotor tends to align to the d-axis with the rotating magnetic field produced by the stator. The magnitude of this torque depends on directly of the difference between the d-axis and q-axis inductance.
Awesome. What is the purpose diagram of the synchronous reluctance motor, and could you explain it to me?
In DQ components terms, the electromagnetic torque is identical to that of a conventional synchronous machine. The power factor of a synchronous reluctance machine is lower than that of an induction motor of the same power and speed. This is because as there is no winding in the rotor, the stator must carry a highly inductive magnetic current.
How can the value of the power factor be determined? With the solvency radius, even with solvency radius of the 7 or 8, the maximum power factor will only be slightly above 0.8. Is there any record comparing the synchronous reluctance motor and an induction motor?
The efficiency of the synchronous reluctance motor is higher than of the induction motor because the rotor losses are eliminated and speed is zero.
At the beginning, a permanent magnet as a synchronous reluctance motor was machined. What's the difference? Does it work different?
The stator of a permanent magnet assist synchronous reluctance motor can be the same as that of an induction motor to reduce cost. The difference lies in the rotor, where permanent magnets are inserted inside each slot. This configuration combines reluctance with magnetic support of that magnets, and its design considers the arrangement, quantity, material, and dimension of this, in addition to elements such as ribs and flux barriers, like this picture shows it.
What changed when using such magnets? The solvency of the motor and the characteristic of permanent magnets influence the performance of the permanent magnet assist synchronous reluctance motor. The magnets could be ferrite of rare earths. Rare earths magnets have less rise of desmagnetization due to the remnant flux density, which is around 1.3 Tesla. How is the torque affected? What is the effect of the permanent magnet?
The torque produced by permanent magnet is determined from this equation. I the torque lambda pm APM as observed in this equation, where lambda pm are the flux linkages caused by permanent magnets.
Well, what implication does this have on the phasor diagram?
The permanent magnet assist synchronous reluctance motor improved upon the standard synchronous reluctance motor by incorporating magnets, which introduce the electromotive force E sub Pm. This shifts the voltage factors V sub S from the second to the first quadrant, this significantly increasing the power factor cos V from 0.5 to 0.8 with ferrite and exceeding 0.9 with neodymium iron boron, placing magnets in the Q axis reduce L sub Q by opposing stator flux, which despite a slight drop L sub D due to saturation, greatly increasing silencing. This leads to an increase in torque density and motor efficiency. Furthermore, the improved power factor reduced the VA power required by the BFD, decreasing system size and cost, and benefit particularly enhanced by using low-cost ferric magnets.
To summarize, what are the advantages and what are the disadvantages? Principal benefits: higher efficiency, increased torque per unity of volume, increased power factor, lower VA capacity of BFD, reduction of its dimension, and lower cost of the BFD. Disadvantages: increased cost and some manufacturing difficulties, rise of magnetic desmagnetization, and magnetic losses. The economic side, what does it have?
A tractor magnet motor has a higher upfront cost. We must look at the benefit. You have to evaluate the inter-system included drive using net present value. Studies show that long-term energy savings cover that investment difference, making the efficient option the most portable one. This investigation is currently reflect of the power factor and efficiency of each test motor.